Quick hello to everybody who's joined already. We'll start in 2 minutes. Hello, everybody. Welcome back to our Test Science Conference 2. This is the second part of our data analysis session. I'm Max Gunter. I'm currently a Taurus Fellow here at MIT, transitioning into a new role as an ESA Fellow at the European Space Agency in the Netherlands in the coming weeks. And I'll be the chair for the second part of the session as well. And just want to remind you, if you have any questions, any comments, anything you want to ask the speakers after the talks, please post your questions in the Slack channel. Don't be afraid to already post some questions that pop to mind maybe towards the end of the talk that haven't been addressed yet. And other than that, we have 3 splinters after the session that I want to point out. You'll see them in the program on the website or in the PDF. We'll have an atmospheric characterization splinter in room 1. We have FFI pipelines in room 6, and we have planets around young stars in room 7. And with this, we'll start the data analysis. discussion and the talks. And we have two talks by Michael Higgins and Tim White. And Michael will kick us off with a talk about disentangling blended variable stars in TESS photometry. And Michael and Tim, after 10 minutes, I'll give you a polite 2-minute are left warning. And after 12 minutes, I'll give you another polite warning to come to the end. And then we'll have 3 minutes of Q&A and pass over to next speaker. With this, Michael, the stage is yours.
Great. Thank you. My name is Michael. I'm a PhD student at Duke University, and I'll be talking about a program for localizing variable stars in TESS photometry. So on the right here, I've provided a target pixel file image where I'm just plotting the flux at a single timestamp and overplotting these little white dots, which are representative of Gaia sources that are 18 mag or brighter. And so what we can see in a single TPF is that there are a lot of stars, and often stars that are relatively close together and being within the same pixel of each other. And the reason that I'm showing this is to sort of display that blended light from nearby stars is unavoidable in TESS photometry. It's important to identify where signals are coming from and what source is producing them and localizing where they are. And so with the large pixel scale of 21 arc seconds for TESS, there's not much great spatial resolution to work with. And the solution to that is the software that we've written. And so it's really easy to use. It just requires a user input of signal frequencies they want to locate and the TPF or target pixel file information. And so the way that it works is that we fit amplitudes of each of the signals in each pixel of the target pixel file. And essentially, we're able to use TESS's high frequency resolution to make up for its relatively low spatial resolution when it comes to identifying the location of source stars. And so I mentioned that this should be used in really all TESS analysis because it's impossible to avoid this blended light problem. And from a broad scope, you can use this program to confirm whether variability comes from the source you intend to study. An example is if you have a light curve with planet transits and you see additional variations, you want to know where those variations are coming from. Are they from the planet hosting star? Are they outside your aperture? Where in the target pixel file are they located? And then on a very specific sense, you can check whether the signals of interest that you want to look at are coming from the same source by testing each signal individually with this program and comparing the results. And so what I have here is I've simulated a single star in what would be a TESS target pixel file, for example. And this star is variable at a once per day frequency. And in the red boxes, I've identified the aperture, the target aperture for this star. And on the left, we can see the aperture periodogram, and we'd see what we'd expect from what I described. We see power at this 1 per day frequency. But we're interested in multiple stars, not just one. So what happens when we introduce another star to this, and this star is located outside your target aperture? So I've now simulated a second star next to it that has all the same characteristics. The only difference is now it's variable at this 10 times per day frequency. And so what we can see in the same target aperture is we still see this power from the target star at this 1 per day frequency, but now we see a significant signal at this 10 per day frequency. But this signal isn't necessarily related to this target star or this aperture. It's light being blended into that aperture that we're looking at. And so that's what we're essentially trying to disentangle the blended light from each other. So what we can do is we can look at the light curves. And for the case of a single star, it's simple. We only saw one frequency that we're interested in, and that's that 1 per day cycle. So we fix a sine wave for 1 per day, and we allow this sort of offset in the y direction for flux, and we fit the amplitude, the offset, and the phase. We get something that looks like this. And then for the 2-star system, we actually saw 2 signals we wanted to see, one from the star inside the aperture and one from the star that is blending light into the aperture. And so we can do the same thing, but for both of those signals, fitting a phase, an amplitude, and an offset. for each of those frequencies, the 1 per day here and the 10 times per day here. And then what we can do is we can use this phase information we got from our aperture fit to inform how we can fit each pixel in the target pixel file. And the reason that we do that is if light is variable from a single source, then within the aperture, that phase is going to be same regardless of what pixel it's in if it's from that same source. So we can do that. And we go through each pixel individually and we fit a sine wave and we look for the amplitudes that are at that particular frequency and phase that we found in the aperture. And so when we do that for the 1 per day signal, we get sort of an amplitude heat map that is centered at where that star is located. And we see amplitude errors that are distributed like the flux. And when we do that for then the 10 per day signal, so in the program, you give it, hey, I want to find where this 10 per day signal is. You get this amplitude map that looks like this, which is, again, located at the source of where that 10 per day signal is, and with amplitude errors that are distributed like the flux. And so the way that we use this information is we then use a pixel response function model. And Keaton Bell has developed some code that's pip installable called test_prf. And essentially, it looks at the CCD, the cam number, and the pixel row and column, and generates the PRF model for your particular target pixel file. And in this case, I simulated it with a Gaussian PRF. So that's the PRF I'm using to fit. And so I use this fit to do a chi-squared minimization to identify the location of the source of this amplitude variability. And we get a final fit result with this red X located directly on top of the star that we wanted to fit, and with a precision that is better than 1/10 of a pixel. So we're able to get precision that is smaller than the full width half max of the Gaussian that we've simulated for our star PRF. And on the topic of precision, we want to know, how precise are we as a function of some metric? And the metric we're using is amplitude over mean amplitude. If I go back to the periodogram, the amplitude over the mean amplitude is simply the amplitude of your peak signal divided by the mean amplitude in your periodogram for your aperture. And so we did that, and we simulated 1,000 different realizations for a single star at varying different values of amplitude over mean amplitude. And we see that our software predicted X and Y standard error very closely match our observed X and Y standard error from our realizations. And the standard error is around 1/10 of a pixel. Then on the right, we see that we achieve Gaussian statistics for our simulated data at a amplitude over mean amplitude of 7.5. And for reference, for a test image, or light curve and periodogram, a value of 5 for your amplitude over mean amplitude is sort of your threshold for even detecting that signal. So just above the threshold for detecting the signal, we achieve 100% of fit success. And so in terms of how precise we are as a function of amplitude over mean amplitude, we get a better than 1/10 of a pixel precision when the amplitude over the mean amplitude in the aperture is greater than the 7.5 value. And then, but we're curious about other stars. So how do nearby stars affect the precision? So we looked at that as well. And so we simulated another 1,000 realizations, but this time for different separations between the stars. So now we've moved the stars from being directly on top of each other to slowly being further and further apart. And what we see is that our fitted standard error and in the X and Y direction are follow really closely to our observed standard errors in the X and Y direction. We also noticed 3 other sort of features. First being that at separation of 0, they converge. The X and Y standard errors are the same, and that's just because they're overlapped. And then in the middle section, what we see is that since we're moving the stars in the X direction, we see an increase in standard error in the direction of displacement. So as that flux spreads out, our code is actually able to identify that, yes, there is in fact an increased error in that direction of separation. And then again, at a significant enough separation such that these stars are completely separated, we see that they converge again at the same standard error, since they're completely separated. So the result is that we get slightly less precision in the direction of separation, but the fits are still reliable. And so now looking at some real data, this image was on the first slide, and now it's come back. Because what's significant about this image is this star right here is a white dwarf in the center of a planetary nebula. And this is from Corsico et al. Paper. They've identified this star. And they found these harmonic frequencies that were indicative of an eclipsing signature. And so they mapped those. And then also these high-end frequencies that were the pulsations of the white dwarf. And they want to know where on the sky or where in the TPF are the eclipsing signals coming from and the pulsating signals coming from. And mind you, the aperture for this, the aperture for the target is this like 2x2 box here. And so what we did was we plugged into our code these frequencies, and then separately we plugged into these frequencies, and we got a result that looked like this. So when we looked at where the location of these eclipsing signatures are coming from, we fit it to one or two of these stars here. That is very clearly outside and not related to the white dwarf that we were looking at. And we can see when we look at the light curve for this particular pixel, we can see the eclipsing signature pretty apparently. And when we look at the pulsating frequencies, the higher frequencies, and fit where those are, we fit it directly on top of the white dwarf. And when we look at the pixel there, we can see that the eclipsing signal is not so present in comparison. And just for reference, this is the picture in terms of flux, what it looked like. So this is amplitude space, and then this is the flux space. And we can see that the white dwarf pixel isn't even the 10th brightest pixel on this image. And this this identified pixel is also really not that bright compared to these other two contaminants. And so the topic here is that in general, this blending of light, it's hard for us to identify when it's happening, but it's easy for us to use this code to clarify and make sure that we're not letting blended light affect our photometric analysis.
Michael,
Yep.
You have 2 minutes left.
Okay. And we will have more information on this in a paper that you can look for in task review soon. And it's also a package that you can install now called Test Localize, and there's a tutorial on the GitHub. And just to reiterate sort of what's going on here, we take variable sources that can't be resolved spatially, and we resolve them in this per pixel frequency space. We take the high frequency resolution of tests, and we're able to inform our decisions on where the local source of variability is coming from for particular signals that we're looking at. So we fight back against this test's large spatial resolution problem. And another takeaway is that we can pinpoint locations of variable stars to better than 1/10 of a pixel for all but barely significant variations. And then just to reiterate this fact that blended starlight is really common in test data. And it's apparent in the example that I showed that it should be a staple to check and make sure that the signatures that you're looking for are related to the source that you're interested in. And checking for the source of variability should be a standard step in a test analysis. And yeah, I can take questions now.
Brilliant. Thank you very much, Michael. I'll applaud again on behalf of everybody in the audience. About 176 people watching for the afternoon session. And while Josh Pepper is typing a question in Slack, I can kick off with Josh's question is just up. I'm going to take it. How limited is this technique to periodic sinusoidal variability as opposed to punctuated periodicity or stochastic variability?
How limited? So since we are looking at strictly fitting sinusoids, if you were to look for trying to do this sort of thing for a transiting signal or something like that, you wouldn't have much luck. So as long as the signal that you're interested in can be displayed in the light curve as a sinusoid fit, this method should work.
Okay. And a few more questions are incoming, but I was curious about, are you using any priors? Like I saw all the points in your plots, which are probably taken from Gaia.
Yeah, no, we aren't using any
means,
priors.
Do you think like that's potentially something to look into? Is there any additional thing that you could gain from using Gaia priors or using like any other known sources, etc.?
I would say that the power of this is that you don't need priors. So if you don't have the Gaia data or whatever, this is just strictly looking at the data that you have from tests and localizing what that signal's from. So for example, if there is something that isn't logged on Gaia for whatever reason, this can still localize where in the target pixel file this source is located. But we do provide sort of a checklist of what Gaia sources are closest, but we don't use them as priors.
Great. There's two more questions which are somewhat could be related. First by Jonathan Labadie-Bartz. Can this be used if you have two sources within the same pixel, but the sources are maybe just a few tenths of pixel separated from one another, so different from the example that you showed here? And I think hand in hand with that goes actually Michelle Silverstein's question. Have you tried applying this to disentangle signals from stars in a cluster, where probably you also have very close by stars?
So we have looked at stars that are really close together. One of which was from a paper, the sextuple star system, I think it was, and those three really close eclipsing systems. And what we found is that within a few tenths of a pixel separated, you still can have the sources within 3 standard deviations. And so the power of it is, yes, you can if the sources are within the same pixel, but the error may be larger for that particular case. It depends on what the program outputs for it.
Cool. And did you try it on clusters as well in that sense?
Not necessarily on clusters. We have done simulations of stars within very close, within the same pixel, and we're able to identify the location of it. But the errors can still encompass the secondary star in that pixel is the thing. So it's to your discretion of whether that star and the errors provided can still encompass the star that you're trying to disentangle it from, if that makes sense.
Great. There's more questions probably coming in the Slack, so please keep an eye on the Slack, Michael. In the interest of time, I'll thank you again on behalf of all the participants and audience members. And
thank you.
We'll go over to Tim. Tim White is going to present to us about observing the brightest stars with TESS. So Tim, once you started sharing your slides, I'll hand over to you, and stage is all yours. Take it away.
Great, thanks a lot. Good everyone. Welcome to Friday, for me at least. Yes, so I'm Tim White. I'm a fellow at the University of Sydney, and yeah, I'm going to talk about how TESS comes the brightest stars. And I really do mean brightest when I say brightest. Just to start off with some acknowledgements. I worked a lot with in this project with Ben Pope at the University of Queensland. So it's kind of a team effort. And also this is part of a wider project within the TESS Data for Toxicology Collaboration, or TDAR. And also I'd just like to thank the TESS team in general for such a fantastic mission. And also in particular, some members of the SPOC, John Jenkins, Doug Caldwell, and Peter Tenenbaum, for their help in me understanding how the calibration works for TESS. Because it turned out this is a story about calibration in large parts. So to get to the bottom of it, I'm going to start with showing how things are easy for a faint star. I think this is faint, although I saw Michael's stars and they are much, much fainter, but anyway. So this one's fairly easy to get a light curve on. It's a fairly small target pixel file image. It's only by 13 pixels. we can see above a flux that's not very, well, it's not saturated at all. And so it's just easy to get a light curve out of this. You define an aperture, add up the flux over the pixels, and you get a light curve. There's some systematics you can correct, and then this is a spotlight curve for this star. Some of you, which we all know, it's Proxima Centauri, if it's kind of flaring a lot. Test magnitude of 7. For me, that's faint. But yeah, that's an easy example for how to get a light curve. Going to a brighter star, about 4 magnitudes brighter, Zeta Tuck. You can see things start to get a little bit different. We've got larger target pixel 5 for 1. This star does saturate. Yep, we've got a log scale here. You can see that where the pixels saturate, you get bleeding along the columns, and that kind of expands out the region where we get flux from the star. But this is still, easy to get a light curve out of by simple aperture photometry. You just need a bigger aperture, and you can sum it up and get a nice light curve out of that. And I think we might be seeing more of this star tomorrow if we're going through this talk. But let's go to really bright star, Sirius, and then now we have Sirius bottoms. For one, there's a very large file, and for 2, and I'm going to take the log scale of the pixel file now. It looks really, really long. These white pixel areas, that's where it's gone negative, and it's gone very negative, and that shouldn't be. And the star itself, that doesn't look right. The counts are way too low. So what's going on here? And it's should be no surprise if we read the data release notes, which everyone does before they look at the data. But I'll explain what's happening here. This is a problem for smear correction. Now, what is smear? These boxes can represent the pixels on our camera, and we've got a star on the center pixel. And as we integrate, we get the counts coming up. But now we need to transfer our image from the imaging array and read it out. And so on the test CCDs, we have the part that's exposed to the sky, and it gets transferred, shifted down to storage, and then it gets read out. And so you have the flux being shifted down the lows, but the star's still there. There's no shadow on test, so there's still light falling on the camera. And so every pixel basically sees everything that's in the column during readout, and so you get a smear in photometry, and that's something that needs to be corrected. Now, it's not hard to do. You just read out more pixels that haven't seen any light during the exposure and only see the light during the readout, and that tells you how much smear needs to be subtracted from your signal. So that's fine, but it fails for really bright stars when they're near the top of the CCD, like Sirius here, because it's bleeding out into where the smear calibration pixels are, and it saturates them, and so the smear gets overestimated. And so that gets subtracted and everything is wrong. But there's good news, because this is just, it is a calibration step. The raw data itself looks perfectly fine. So there's a solution. We just need to don't use bad smear correction in the calibration. So how do we calibrate? So this is the steps in the calibration module. The test one's based on this, and so it's basically the same. This step isn't used in the standard test pipeline. But the smears here towards the end. So the simplest thing would be to do is just wind back from the calibrated image, take out the fat field, take out the bad smear, calculate a good smear for now, and then go forward. But it turns out this is actually hard to do because the actual bad smear is not saved in the capital data. So it's actually turns out to be easiest to basically do a calibration from scratch, going through all the steps. And so I've got some code to do that. So let me introduce you to Mundi. Here's the code. It's open source in Python, and basically recalibrates test target pixel files and calculates a new smear correction for these stars where it's an issue. And it's available on the GitHub. It's also installable if anyone wants to use it. So I'm sure there's a few questions about Mundi. First is, why is it called Mundi? It's a kind of weird name. So it's kind of a long story. It's basically named after an Australian trade union official and environmental activist. And it's linked to Sirius, but in a kind of not very direct way. So I'm not going to go into details, but you want to understand there's explanation in the README. Anyway, that's why it's called Mundi. How does Mundi work? So basically, it tries to replicate the calibration module in the spot pipeline. So starting from the raw data, it does the corrections, so it's fixed, offset, and black. You can see here already that this smear is quite apparent for Sirius here. The corrected black levels, non-linearity and gain. And this next step is not usually used in the standard test pipeline, but what it does is it corrects what you can see here. Is that when you go from a really white to a very faint, relatively faint pixel, you get something called undershoot. And so this next step fixes that. So we include undershoot correction in this. And then comes the smear. We can't use standard smear data, but you can quite clearly see the smear is in the target pixel file itself. And so we estimate it from these pixels at the bottom where Sirius doesn't exist, or whichever bytes that we're looking at. Basically remove the other background stars and just calculate the smear from this and do other adjustments to estimate what the smear should be. And that works quite well, as you can see here. And then a few more other corrections, flat field, and a conversion. And we get a good looking target pixel file for a really bright star like Sirius. That's not the end of the story. Once you've got a target pixel file, you need to estimate the background and then make a light curve. It is not trivial for these really bright stars because you've lost quite often some of the flux off the edge of the CCD. But we've got a code for doing this as well. We developed it for K2, where we get we make the light curve from a sum over the non-saturated pixels like this. So we ignore the saturated pixels and find weights that give it the least noisy light curve. And that gives us something like this for Sirius. There's still some schematics in here. We're working on the corrections for this. So this is kind of a corrected version. For Sirius, and take its power spectrum, it's mostly flat. And I expected Sirius to be pretty flat, but there's also this kind of red noise and maybe some peaks down here, which reminds me of the O and B stars that Dominic Bowman was showing on Tuesday. I don't know if it's the same thing happening here. It's interesting. Something to investigate.
Tim,
yep.
You have 2 minutes left.
No worries. Okay. And it's not just the bright stars that benefit from this program. You can see there's all sorts of faint stars in the same type of pixel file, and they would have been ruined, or they are ruined by the bad smear correction. But we can fix that. Unfortunately, not all of these stars, there's no signal in them, but this one is variable, and so we can get light curves of these stars too. A few other examples, Arcturus. This one doesn't have a bad smear because it's at the bottom of the TPF, bottom of the SSI, but we can fix the undershoot problem it has, and we can see it's nice red giant pulsations. Another example is Polaris, hormone Cepheid variable, and so it would be interesting to the amplitude and frequency of Polaris has been observed to change over time. So it'd be interesting to see how this shows in test data over time. And a final example, one close to the heart, is Procyon. You can see the Mundi TPS with the smear issue that Procyon has. And this is an old friend for the solar astrocosmologists, because it was the first star other than the Sun that we detected solar-like oscillations. And this was done by Ken Brown and his team. Although they hedged their bets on the title here, possible oscillations, but shown to be true. The early space-based photometry with the most satellite tried to find oscillations in Procyon, but didn't find it, and this was quite controversial at the time because this was meant to be the star where we should find it. But it wasn't found initially. It was found later in most data, but not straight away. And then there's been this great ground-based campaign with 11 telescopes, and you can see the oscillations quite clearly in this data. But it turns out really why it was hard with most, and it's because it's an F star, and the mode line widths are quite broad in F stars. So it's quite hard to see compared to a cooler G-type star. And to make the mode identification, it's quite clear in cooler stars, but here knowing which mode is which is quite difficult. And so for Procyon, we don't actually know yet whether the mode identification is this way or the other way. And there's a bet about it between Tim Betting and Jan Christian Dalsgaard. And so we'd like to solve that bet and also learn more about the star. So here's the test target pixel file. Here's our light curve. And you can see from the power spectrum that we do see the solar oscillations quite clearly in our data. And here's the shell diagram for this compared to the ground-based. And so yeah, we've got a very clear protection. I don't think we can decide the mode identification from this data alone, but we are getting more of it as it continues. So hopefully we can damage that. So in summary, with our code with Monday, there's no star that's too bright for tests. We will make the light codes available to the community through Marston at TASOC. Our codes are available on GitHub and also they're installable. And anyone who wants to contribute, still work in progress, then that's welcome. Yeah, thanks everyone.
Yeah, thank you very much, Tim. We have time for 2 or 3 questions. We're starting off with Chris Halminiak, who's asking, have you compared your light curves with data for bright stars observed with the bright satellites?
Not as yet, but yeah, we should. Yeah.
Cool. All right.
Yeah. So yes, that's pretty much it. Yeah.
Nice. I completely forgot. Thank you very much for the great talk, by the way.
Thanks.
The questions are already coming in, so got very caught up by that. Josh Pepper is asking, is there a particular TMAG limit where Monday is required?
It kind of depends on where the star is on the full-frame image. So typically it's kind of first magnitude stars that kind of get to the top and bleed up into the smear, the upper register of the CCD that cause issues. But the closer a star is to the edge, the more likely that is to happen. And so, for example, get Gamma Crucis, which is on the top star of the Southern Cross. That's kind of right in the middle of the CCD and kind of doesn't actually bleed off the edge. So that one is not actually required, although it does fix the undershoot issue. But yeah, roughly about first magnitude, I'd say. So it ends up being about 100 star, like, if you get 2 or 3 stars per sector, that's really useful.
I had a question that's kind of like going a similar direction, not for brightness, but generally, like, do you see a difference between different test sectors and like the amount of scattered light? Does that determine something, or also like how close you are to the edge of the CCDs, or at a certain camera shows slightly different effects? Do you see anything like that? Anything systematics or instrument related? I
haven't noticed anything yet. We've only recently got this off the ground, and we're still trying to kind of, at the moment it's kind of bespoke, and Ben's working on kind of industrializing this to run on all the stars. And so we haven't yet kind of looked at enough sectors, I'd say, but yeah, I'll let you know.
We have a bunch more questions coming in the Slack, so I encourage you to hit up the Slack and answer the questions there. But I thank you very much again for this really great talk on behalf of the audience, and likewise for Michael and both you for these engaging discussions. And with that, I want to point out we have 3 splinter sessions coming up now. We have the atmospheric characterization session in room 1, the FFI pipeline session in room 6, and the planets around young stars in room 7. So you'll find the individual Slack links for each of these rooms, 1, 6, and 7, in the PDF document that's linked on the website program. And with that, thank you very much for our speakers. Thank you for everybody contributing to the data analysis section. And we'll see you all in the splinters and tomorrow. Take care.
All right, so some people are leaving. So just for context, this will now turn into the room for the atmospheric characterization splinter session. So we'll just break for maybe half a minute or so, so people can just find their way in and out. And then let me just quickly introduce myself. I'm Tansu Dailan. I'm a TESS postdoctoral associate, and I'll be chairing the atmospheric characterization splinter session today. Again, just to reiterate, this is room number 1. So this is the right place if you want to hear about the atmospheres instead of FFIs or, I guess, young planets. And yeah, we have a great lineup all about atmospheric science enabled by TESS. And couple of reminders: if you have any questions at any time, please write them in the Slack channel. I will read them out loud so that our speakers can answer at the end of their talks. For the speakers, please try to finish your talk 3 to 4 minutes before the end time, so that you will have enough time to answer the questions and to do the switch over. And yeah, I think the number of people is kind of stabilizing, and maybe we might want to get started without losing too much time. So we will start the session actually with a overview talk, so that we all first agree on the nomenclature as well as the broad view of atmospheric science enabled by TESS. And that will be given by Tom Evans from MIT. So yes, he's here. So Tom, the floor is yours.
Okay, thank you, Tansu. Okay, so thank you, Tansu, and hello, everyone. So I'm going to be talking about the important role that TESS is playing for atmospheric characterization. And this image here is an artist's impression of the sub-Neptune K218b, which orbits an M-dwarf and is quite analogous to the best targets that TESS is discovering for atmospheric characterization. Until now, for atmosphere observations, we've mainly been using Hubble and Spitzer to observe hot Jupiters, but we're now on the cusp of a new phase with the launch of Webb later this year, which will give us greater sensitivity and a much broader wavelength coverage than before. And this is also the case for the recently commissioned CRIRES Plus spectrograph on VLT, along with a number of other newer shell spectrographs, which in principle can be used to Doppler resolve the spectral features of planetary atmospheres from those of the host star. And we have surveys like TESS and Speculus that are detecting the best nearby targets for atmospheric characterization. TESS is mainly sensitive to spectral types down to mid-M, whereas the Speculus observing strategy is optimized for late M stars down to ultra-cool dwarfs. In a few years, the Twinkle satellite will also launch, and at the end of the decade, Ariel is scheduled to launch, and both of these satellites will be dedicated to conducting a survey of exoplanet atmospheres using transmission and emission spectroscopy. TESS is going to be our most important source of atmospheric characterization targets for the foreseeable future, at least in terms of sheer quantity. But what is it that makes TESS planets so good for atmospheric spectroscopy? For this purpose, there are two useful metrics laid out in Kempton et al. 2018 that indicate how the detection significance of an atmospheric signal should vary with system properties: the emission spectroscopy metric and the transmission spectroscopy metric, or ESM and TSM for short. Without going into each term in detail, the ESM essentially quantifies the ratio of the planet's emission to the stellar emission using black bodies to approximate each, while the TSM quantifies the transit depth and puffiness of the atmosphere, more or less. Both metrics also scale with the magnitude of the host star, because this determines the signal to noise with which we can measure a relative change in the intrinsic system brightness caused perhaps by an atmospheric signal. So broadly speaking, for atmospheric characterization, we can expect the highest signal to noise for systems with a bright host star, a large radius ratio, a high planetary temperature, and a low planetary mass. And TESS planets really deliver on the first two of these criteria, and in fact do so to such an extent that we can relax the constraints on planetary temperature in particular, and in principle push into the interesting lower temperature regime below around 1000 Kelvin, while still maintaining a good signal to noise. So here's the population of currently known planets with measured masses, showing their equilibrium temperatures and radii, with points color-coded by the host star spectral types. You can see that we tend to find hot Jupiters around early type stars, shown in yellow and blue. Smaller, cooler planets, on the other hand, tend to be found around later spectral types, including M dwarfs. And for the purpose of atmospheric characterization, we can remove those planets failing to meet the minimum TSM and ESM thresholds laid out in the Kempton paper. And what this leaves us with is a sample of 216 currently known planets suitable for atmospheric characterization. And we expect TESS to add many more planets in the coming years. For now, though, we can convolve known planet population statistics from Kepler with the observing strategy of TESS to predict what TESS is likely to produce by the end of its extended mission. And here's what we get. All up, we expect an additional 250 or so planets suitable for transmission and emission spectroscopy, so roughly doubling the current sample. And if I fade out the non-TESS planets, you can see that the biggest contribution of TESS is for sub-Neptunes and super-Earths cooler than about 1000 Kelvin, particularly orbiting M dwarfs. As we move into this lower temperature regime, thermochemical equilibrium increasingly favors gases like methane and ammonia, but at the same time, chemical reactions are slowing down, and it becomes easier for processes such as atmospheric dynamics and photochemistry to drive the chemistry of the atmosphere out of equilibrium. So TESS is opening a rich new chemistry regime to explore and try to make sense of. TESS is also uncovering plenty of multiple systems in which more than one planet is suitable for atmospheric characterization. Of the 147 TESS planets confirmed so far, 73 of them are in multi-transiting systems. And in 2018, Sarah Ballard predicted that around 20% of M-dwarf systems discovered by TESS would be multis. And I by no means have looked into the numbers properly, but based on what we seem to be seeing to date, it seems possible that even this was an underestimate. But in any case, the discovery of multis around bright stars like HD 108236 shown here opens the prospect of comparing atmospheres formed in the same stellar system. So campaigns to follow up TESS planets for atmospheric characterization are now well underway. And here I'm summarizing planned observations to be made with Webb and Hubble, which are our top space-based facilities for exoplanet spectroscopy. The left panel shows targets to be observed in transmission, and the right panel shows targets to be observed in emission. All of the Webb cycle 1 targets are shown with different symbols indicating the type of observation, and TESS planets are highlighted in green. Also shown as black crosses are test planets to be observed with Hubble. So aside from a phase curve for TOI 2431b, all of the Hubble observations will be transits. So most of these will in fact be made in the UV. For Webb, there's also quite a heavy bias towards transits, and it's clear that the major contribution from TESS is for sub-Neptunes and super-Earths with temperatures around 1000 Kelvin and cooler, as expected. Now, the pace of test planet confirmations is still increasing, and I anticipate we'll see plenty more test planets on these plots as we move to Webb cycle 2 and beyond. But already though, it's clear that TESS is having a major impact on the community's atmospheric follow-up efforts. So that's the future, but how about atmospheric characterization work that's already been published? Until now, publications have come from two sources: the TESS photometry itself, mostly for previously known hot Jupiters, and at longer wavelengths, Spitzer follow-up photometry of TESS planets. So starting with Spitzer, at the last TESS conference, Laura Kreidberg presented a phase curve measured for the hot rocky planet LHS 3844b. And these data are shown on the left here, and they allowed a global brightness temperature map to be inferred, shown on the right. The authors were also able to deduce that LHS 3844b almost certainly lacks an atmosphere, which is a useful measurement because a big open question is how many rocky planets actually have and retain thick atmospheres, particularly those orbiting M dwarfs like LHS 3844. And I believe the only other rocky planet with a published phase curve is 55 Cancri E, really emphasizing that measurements like this one have basically not been possible prior to TESS finding more rocky planets around bright stars. And moving into the Webb era, I want to briefly mention the work of Daniel Cole, Megan Mansfield, and colleagues, outlining how secondary eclipses can be used to determine which of the rocky planets discovered by TESS have atmospheres, much more efficiently than expensive phase curves like this one. And the Cole paper in particular reports that in principle, with Webb, we should be able to perform such measurements for about 100 rocky TESS planets. So TESS is really delivering us a great sample to test theories of atmospheric escape for rocky planets. Another set of Spitzer observations made for a TESS planet was published by Ian Crossfield, Diana Dragomir, and collaborators. The target was LTT 9779b, a hot Neptune with an orbital period of less than a day. The measured phase curve data are shown up the top here, and down the bottom, the best fit to the 4.5 micron data is shown in red compared to a couple of general circulation model predictions. While the overall agreement with the data isn't too great, the lack of measured hotspot displacement from orbital phase 0.5 is arguably in better qualitative agreement with the higher metallicity model shown in blue. On the right, the day-side emission derived from the secondary eclipses is shown, favoring carbon monoxide absorption at 4.5 micron and a temperature profile that cools with decreasing pressure. TESS photometry itself has also been used to directly characterize atmospheres, with phase curves now published for a considerable number of hot Jupiters. And shown here are two of the standout examples, WASP-18b on the left and WASP-121b on the right, both ultra-hot Jupiters with day-side temperatures above 2500 Kelvin. I've listed other published TESS phase curves down the bottom, and in particular, Ian Wong and colleagues have been systematically analyzing phase curves for all the known hot Jupiters observed during years 1 and 2 of the TESS mission. Very briefly, here are some examples of the kind of constraints that can be placed on atmospheric properties by measuring hot Jupiter phase curves with TESS. First, this is the emission spectrum of WASP-121 from Bourier et al., with the TESS point shown in pink, strengthening the evidence for enhanced emission at shorter wavelengths compared to the best fit blackbody shown by the dashed line. While the source of this optical emission remains unknown, possibilities include negative hydrogen ions and vanadium oxide. Phase curves also allow constraints to be placed on the atmospheric albedo and recirculation efficiency of the atmosphere. In this example, again for WASP-121, the data favor a low albedo and poor heat recirculation efficiency from the day side to night side hemisphere. And with a respectable sample of TESS phase curves now, it's possible to start searching for trends in the population by plotting inferred properties such as albedos against day-side temperatures as shown here. From their systematic study, Wang et al. Find evidence for a rise in albedo between temperatures of 1500 and 3000 Kelvin. And one possibility they speculate on is that this might have something to do with refractory condensates like aluminium oxides becoming increasingly significant at the western dawn limb of the atmosphere as you go to higher temperatures, but this is still very much open to interpretation. Now, I'm aware that Daniel Apai will be talking about this work in more detail shortly, but it's really worth highlighting that some pretty amazing insights can also be extracted for brown dwarf atmospheres from TESS photometry. But right now, though, I'm short on time and I'll leave it to Daniel to say more about these results. And finally, I want to very briefly look forward to the 2030s and beyond, when giant segmented mirror telescopes such as the ELT and possibly next generation space telescopes like Origins will conduct searches for atmospheric biosignatures. Using the techniques of transmission and Doppler resolved spectroscopy, these observatories will require a sample of rocky planets orbiting in the habitable zones of nearby M dwarfs. And the planets discovered by TESS will likely be the foundation of this sample. To illustrate this, here's one last scatter plot, this time showing the known transiting planets orbiting stars bright enough for detailed follow-up, with orbital period along the horizontal axis and stellar effective temperature along the vertical axis. I've split the planets themselves between those discovered by TESS in blue and all the rest in black, with solid circles showing likely rocky planets and open circles showing likely gas-dominated planets. As you can see, we're starting to find planets in the green habitable zone, including a few rocky planets, most spectacularly with the TRAPPIST-1 system, as well as a few others, including TESS's first, TOI 700d. Like before, we can also add in the planets that TESS is predicted to find, and that's what these orange points show. And focusing on the green habitable zone for biosignature searches, TESS is expected to deliver a modest but important sample of rocky planets. This, along with perhaps a dozen or so planets from Speculus, is likely to form the sample of transiting planets best suited for an atmospheric biosignature survey. Although such a survey won't be possible until next decade at the earliest, it's another example of how important the planets TESS is uncovering are to our overall atmospheric characterization efforts, both now and for many years to come. Thank you.
Thanks, Tom, for a very nice overview. So let's see. You can just write your questions in the Slack channel. I don't see yet any questions, but please feel free to indicate any questions. If not, I'll start asking, but I'll first pause to see if there's any from the audience. Okay, so let me then just start by asking my question. So you indicated kind of in the beginning or towards the beginning of your talk that the chemistry is slowing down for planets that have lower equilibrium temperature. So I assume that means that some assumptions that we typically do that we make for planets, atmospheres, or dynamics where the dynamical timescales are always shorter, so faster essentially, than chemistry, we just cannot make those assumptions anymore. Does that introduce any modeling challenges to making any inferences about the atmospheric characteristics?
Yeah, for sure. It's really challenging to simultaneously model dynamics, say in a 3D general circulation model, and also allow for a chemical kinetics code to track the changes in conditions that a given parcel of gas is experiencing as it moves through the atmosphere, and recompute the chemistry in that way, rather than assume that local thermodynamic equilibrium persists at all points in the atmosphere. So simultaneously tracking the motion of gas and solving for the chemistry is very computationally expensive, but groups are starting to do that. So it is happening, and I think it's going to be really important, particularly as we start observing these cooler atmospheres, to correctly interpret what we're seeing.
Yeah, I think it's a computationally interesting problem. I see one question from Brian Jackson. So he says, could you say more about the method of determining whether a rocky planet has an atmosphere by looking at its eclipse, specifically Cole et al. And Mansfield et al. 2019?
Yeah, so I think this method works by making assumptions of what albedos are possible for a rocky surface between the temperature range of 300 and 900 Kelvin, based on geochemical arguments, and comparing the thermal emission that you measure from the planet to the thermal emission of a body with an albedo in that range. If it was just absorbing the energy from the host star and re-radiating immediately. And if you find that the measured thermal emission is lower than that theoretical prediction, then it would indicate that there's an atmosphere present to be redistributing some of that incident energy to the night side hemisphere. It does seem to rely on a few assumptions about the geochemistry of the surface of the planet, but the paper certainly seems to consider those in quite a lot of detail, and I would assume is quite sound theory.
Thank you. Okay, so he has a quick follow-up question. Can you remind me which small rocky planets are thought to have atmospheres? 55 Cancri E, maybe?
Yeah, I think that remains a fairly ambiguous case. I think 55 Cancri is a bit controversial still. There has been a claim of a hydrogen-rich atmosphere based on a slope seen in the wide field camera 3 transmission spectrum. But yeah, I think that's still not universally accepted as a solid detection of an atmosphere for that planet. I think there could also be some arguments from phase curve measurements too, but I don't know those off the top of my head, sorry. But I would say it's certainly not conclusively determined that 55 Cancri has a significant atmosphere. And I'm not aware of any others, actually. So I don't think, to my knowledge, there's been a definitive detection of a significant atmosphere. I guess there was LHS 1140b recently showed hints of a spectral absorption feature in the wide field camera transmission spectrum, but again, the signal to noise is quite low, so it's still a bit of a borderline case.
All right, thank you so much. So let's thank Tom for this nice overview talk. And then we will move on to the next speaker. So the next speaker will be Eliza Kempton from University of Maryland. And she'll talk about the TESS Atmospheric Characterization Working Group, its operations, and its, I guess, vision and mission. So thank you, Eliza, and please take it away.
Okay. Get my screen set up. Oh boy. Okay. Can you see my screen?
Yes, we can.
Not set up optimally for me, but we'll be okay. All right, so thank you, Tansu, and thank you, Tom, for a really nice summary talk there. I'm going to be giving a slightly different talk. This is not a science talk, but rather more of an informative talk about the activities that the TESS Atmospheric Characterization Working Group has been undertaken, and I am currently serving as the chair of that group. The entire membership is listed on this slide. Okay, so like the other TESS working groups, we have a group charter. A little bit of history first. The Atmospheric Characterization Working Group was originally envisioned as a group to conduct pre-launch activities for maximizing TESS's impact on exoplanet atmospheric studies. That's wording directly from the original charter of this group. When I took over now about a year and a half ago, we realized that given that at the time the prime mission was almost over, we needed to re-envision what the key goals of our working group would be. And so now going forward, the role of the ACWG is to ensure the successful legacy of the TESS mission, specifically relating to atmospheric characterization of TESS discovered exoplanets. So basically we heard about all of the wonderful atmospheric characterization science that is being undertaken with TESS planets in Tom's talk just now. The goal of our working group is really to enable that science. Okay, and to achieve this lofty goal, we've broken down our work into 4 key tasks. They're listed right here. Task 1 is identifying the most promising TESS discovered exoplanets for atmospheric characterization. Task 2 is to coordinate with other TESS working groups to enable atmospheric characterization efforts. Task 3 is to provide a venue for research groups to coordinate their atmospheric characterization observations. And task 4 is to advocate for programs and procedures that will lead to successful atmospheric characterization of TESS discovered exoplanets. And none of these tasks lives in a vacuum. They are highly interrelated with one another. And we have a great set of task leads, including our first speaker of the session and our organizer of this session, who are working to manage these 4 tasks and also working very closely with one another at the intersection of these tasks. All right, so with my remaining time, I'm just going to go through in a bit more detail what we are doing to execute these 4 tasks so far. So task number 1, led by Tansu, identifying the most promising TESS discovered exoplanets for atmospheric characterization. We have now included 2 fields in the ExoFOP TESS TOI list. If you go to that website, where you can see the ESM and TSM atmospheric characterization metrics, the signal to noise metrics, allowing you to rank these all of the TOIs by their expected signal to noise in transmission or emission spectroscopy with JWST, and then apply your own threshold cuts at will. And Tansu and Natalie Guerrero in particular have put together a very nice website for our working group, which I encourage you to check out. Someone could post that in the Slack, actually, or I'll post the link after this talk. Our website has a bunch of resources from our group, and in particular, we have now a web-based community input form where members of the community can identify specific atmospheric characterization targets that they would like to see prioritized by the community. And we're really using this as a way for the atmospheric characterization community to communicate to, for example, the TFOP group about targets that they would like to see fast confirmation and follow-up done on. Okay, task 2 is our task of coordinating with the other TESS working groups. Diana Dragomir is leading this task, and here we are appointing liaisons between our own working group and the other TESS working groups so that we can coordinate on topics of mutual interest. In particular, Diana, as the liaison appointed to TFOP, has been responsible for mitigating the communication with ACW and TFOP surrounding these community input targets. When individuals use our web-based form, Diana can then communicate targets of interest to TFOP and get TFOP in touch with those individuals who have expressed interest in particular atmospheric characterization targets. Task 3, providing a venue for research groups to coordinate their atmospheric characterization observations. We've attacked this task by providing a number of resources on our website that we believe will hopefully be of use to the community. The first one is a spreadsheet that was put together by Bjorn Benecke and his group that lists off all of the approved JWST transiting exoplanet targets and various information about those approved observations. And the plan is to continue to keep up this spreadsheet into future geo calls, and then we'll probably add some more fields once the observations are actually being executed as well. Additionally, Tom Michael Evans has put together a set of these matrix plots that identify over a range of parameter space the top atmospheric characterization targets as defined by their TSM and ESM signal to noise metrics. We have a couple of versions of these matrices on our website. This one in particular that I'm showing here is really targeted towards the test follow-up community, in that this is a matrix showing the top potential atmospheric characterization targets among the unconfirmed TOI. So these are all planets that remain to be confirmed as true exoplanets for atmospheric characterization studies. And finally, task 4, our task of advocating for programs and procedures that will benefit the atmospheric characterization of TESS exoplanets in particular. Here we have been trying to maintain some active communication with advisory groups, specifically with the STUC and the JSTUC, the HST and JWST advisory committees at Space Telescope and others. We have also, members of our group have also organized now a number of successful talk sessions about atmospheric characterization of TESS exoplanets, including this session right here, organized by Tansu, as well as Tom Beatty put together a AAS session this past winter. Okay, so what can you all do to be involved? If the kind of work that we are doing interests you, you can apply to join the ACWG. We always have an open call for new applicants. Just take a look at our charter, which is up on our website. Also, please do make use of the resources that we have provided on our website. The spreadsheets, the target matrices, and in particular, please feel free to fill out our online form if you have specific exoplanet targets that you would like to promote for high priority within the community or to the TFOP group. And as always, you are welcome to contact our group with any questions or suggestions for activities that we might undertake. You can go via me, or you can email any of the other members of our working group as well. And just one last plug for our website, please do go check out the resources that we have there. Thank you.
Thank you, Eliza, for the very nice talk and a summary of operations. Let's see if there's any question from the audience. Again, I will quickly pause so as to motivate people to ask questions. We do have 1 or 2 minutes. Eliza, maybe you could make a quick remark about the community feedback form we have, and the fact that it could turn out to be very useful if people used that.
Yes, so our community input form, it's really for all of you. If you have a target that you are interested in, but you feel that you require more information about it, say it's not a confirmed planet, or it doesn't have a mass, or you're worried that the ephemeris might be out of date, but you're not a member of TFOP per se. This is the form is a great way to get that communication line open to the TFOP group. And the reason that the form goes to the ACWG and specifically goes to the members of the steering committee of our group is to try to maintain some confidentiality there. We're not going to broadcast to the entire public community that you want to observe this planet with JWST. There's a feedback box, and if you would like to maintain some degree of confidentiality with respect to what targets you're interested in, you can just indicate that to us, and we can help handle that in a sensitive way. So we want this to be a useful resource. We also don't want, we would like to allay any questions about or any concerns about confidentiality of interest in targets.
Thank you, Eliza. I see no questions, so maybe if there's one eventually, you can just respond over Slack. I see Johanna is typing, but I'm not sure if that's actually a question. So then let's thank Eliza again for the very nice overview of TESS Atmospheric Characterization Working Group. So our next speaker is Kevin Heng, and he's joining from a time zone where he will need to sleep very soon, so we put him as early as possible. So he's from University of Bern, and he recently changed positions, I think, so congratulations. And he will talk about albedos and phase curves of celestial bodies. Please take it away.
So thank you for having me. It's late, I'll try to keep my energies level up. I think I don't need to convince this crowd the importance of cloud haze or aerosol formation. It's a long-standing problem. And today I would like to talk about two papers that we just published. One is already published in the ACWG, and the other one will come out in Nature Astronomy in the coming weeks, that I think will move the needle forward on this problem. So the executive summary of these two papers would be that we demonstrated that the fundamental properties of clouds or hazes or aerosols may be retrieved from precise photometry alone. I will try to prove this to you by showing you two case studies. One is of Kepler 7b and the other is of Jupiter using Cassini data. And this is because we managed to derive closed form ab initio solutions of reflected light phase curves. This is the first time that novel solutions have been found analytically since Lambert in the 18th century and Hepke in 1981. This problem was formally and mathematically posed by Russell in 1916, so it's almost a century old. And because these are ab initio solutions, they have no tuning parameters, which implies that they can be used to extract fundamental parameters from data. So now just to remind you for what the various quantities of interest are, the secondary eclipse depth is directly related to a quantity known as the geometric albedo, modulo some geometric factor that's not interesting for us. The reflected light phase curve is the same bunch of quantities, but there's an extra quantity called the integral phase function. This quantity quantifies the shape of the phase curve. So mathematically, what we would like to solve for is we would like to obtain solutions for both the geometric albedo and the integral phase function. And we would like to do this from first principles by solving the radiative transfer equation. Unfortunately, I do not have time to explain all of these steps to you. I wish I had 30 minutes, but I don't. So instead, I'll give you a flavor of the various texts I had to read to get insights on this problem. So for example, Lambert's law goes back to the 18th century. This gives rise to a very idealistic model known as the Lambertian sphere, which observers still use to this day to analyze phase curves. And there's, of course, the wonderful work of Chandrasekhar, who derived an exact solution for isotropic scattering in the so-called semi-infinite atmosphere. Hepke, who is a lunar scientist who studies lunar phase curves, derived a key approximation to Chandrasekhar's solution. And Sobolev published a very influential 1975 textbook and can only be described as a Russian master of radiative transfer. So combining these four insights, we were able to derive these novel analytical solutions. It's not so interesting to this crowd. I think to this crowd, what is interesting are the observational implications of these solutions. So first, let's talk about exoplanet phase curves. Let's use Kepler 7b as an example. And traditionally, the standard practice is that one would fit the shape and the amplitude of the phase curves independently, using a model that's not necessarily physical, meaning that the shape is some parameter, the amplitude is some parameter, and the shape is a bunch of sines and cosines, which you cannot necessarily interpret. With these new solutions, the shape and the amplitude of the phase curve are self-consistently described by a set of physical parameters. For example, single scattering albedo or scattering asymmetry factor, which describes the isotropy of scattering. And the fact that these solutions are analytical also means that you can do the trending and fitting of the phase curve simultaneously. And this is what Brad Morris did for Kepler 7b. So there's a lot going on here, but besides the fundamental physical scattering parameters, we demonstrated for the first time that you can actually retrieve the so-called spherical albedo directly from the optical phase curve, and you can derive a quantity known as the phase integral. Now, moving on to the solar system, and to Cassini data of Jupiter, which was collected in the early 2000s. There's a long-standing puzzle that these phase curves are really cuspy, you can see from the plot, and that classical reflection laws do not fit the data. So classical reflection laws, including the Lambertian sphere, Rayleigh scattering, or the single Henyev-Greenstein are just very poor fits to the data. And for whatever reason, the data has never been interpreted using a Bayesian framework. And again, because the solutions are analytical, the retrievals are really, really fast. They're lightning quick. They're just maybe a couple of minutes. So we were able to do retrievals of 61 Cassini phase curves of Jupiter. And for each phase curve at a specific wavelength, you can extract the fundamental physical scattering parameters, such as the single scattering albedo and the scattering asymmetry factors. And then you can lay them all out on one plot as a function of wavelength, like the bottom. And independently, you can lay down the methane absorption bands. And what's really nice is that it's consistent with previous knowledge, which is that if you look at the third methane absorption band near 0.9 microns, it was known previously that methane absorption is strong enough to make scattering weaker, and this is indeed what we see in the retrieved scattering parameters. You can also interpret this information geometrically. So if you take these 61 retrieved sets of scattering parameters, you can draw the plot on the bottom right. The blue for reference is the Rayleigh scattering geometric pattern. And you can see that the aerosols in Jupiter's atmosphere, whatever they are made of, do not behave in a manner that's consistent with Rayleigh scattering. We can also extract the following properties from the aerosols in Jupiter's atmospheres. They are large, possibly irregular. They're polydispersed, meaning that they are not a single size, but a range of sizes. And you infer this by seeing that the scattering asymmetry factor does not monotonically decrease with increasing wavelength. It's inconsistent with Rayleigh scattering, as I already mentioned. The single scattering albedo is high enough, it's close to 1, that multiple scattering of radiation is really important. And there's a backscattering lobe, whose physical origin we are still investigating. So this is a really interesting data set, and we have a second study to follow this up. And this is my summary slide. If I have 30 seconds, I will just summarize. So we report the discovery of a family of novel ab initio closed form solutions for the geometric albedo and phase curve shape. The first solutions reported since at least 1981, and the general solution to a problem posed about a century ago. The shapes and amplitudes of reflected light phase curves encode really important information on reflection laws and the fundamental properties of aerosols. And hopefully I convince you that precise photometry is potentially more powerful at constraining the fundamental properties of aerosols than precise spectroscopy. And I'll leave you with a thought. One very strong test of whether an atmosphere is cloudy or cloud-free is to test if the optical phase curve is consistent or inconsistent with a Rayleigh scattering phase curve, which has a very distinct shape. Thank you. I'm happy to answer questions.
Thank you, Kevin, for the very nice talk. So any questions? I see someone is typing. Okay, so there's a question from Mauro Barbieri. Very nice talk. Does this method could explain also the opposition effect?
That's a great question. I didn't mention that because it's a little obscure, but this the cuspy, we believe that the literature believes that the cuspiness of the phase curve is precisely due to the opposition effect, which can be explained by two effects. One of them is called coherent backscattering. And since Jupiter doesn't have a surface, the only explanation left is coherent backscattering and not shadow hiding, which is the other explanation. I hope that answers your question.
Okay, any other questions? We have time for one more question. I can squeeze in one. So does this, I guess, when you say amplitude and shape, I mean, one advantage to having amplitude and shape is that initially you think that they would be orthogonal, so would reduce degeneracies in the problem. Is your ab initio solution less or more degenerate?
That depends on the problem. So you can see the posteriors here, but the key advantage is not just reducing degeneracies. The key advantage is that there are no ad hoc parameters that have no physical meaning in the model. So when you fit a phase curve, you usually fit it with a bunch of sines and cosines, and it's difficult to interpret what the numbers in front of the sines and cosines actually mean. And here you have no such problem. All of the quantities are physical.
Okay, that's great. One more question from Brett Skinner. Great talk. How do you anticipate the effects of the phase curve to be similar or different from exoplanets with much shorter distances to their host stars?
I would ask you to stay tuned to a paper that one of my postdocs, Brett Morris, has been working on for over a year. So Brett has taken all of the Spitzer phase curves and all of the Kepler phase curves in existence, and he has run them through he has made a framework made out of these solutions, and he has run all of the phase curves through this framework. And so we were able to reinterpret basically a lot of the results in the literature and also extract all of the scattering properties. The other thing to mention is that this kind of solutions also allows you to bridge the distance between data and GCMs. So you can potentially describe GCMs with these kind of solutions as well. So it's an alphabet to speak to describe both data and theory.
Sounds good. So one last question very quickly from Néstor. This is awesome, Kevin. The Cassini data still shows some residual peaky behavior. Can you explain why this is?
This is also something I'm investigating. I can tell you that if I do not use a so-called double Henyev-Greenstein, a double Henyev-Greenstein was used because the planetary science literature has been using this for many, many years. So I wanted to use the same thing as they used. But a better thing to use is a reflection law that's consistent with so-called coherent backscattering, which I mentioned in the answer to the first question. And when you use coherent backscattering, it fits like a glove. Even near the peak, it just fits exactly. And so now I'm running the coherent backscattering fit through all 61 phase curves again. I haven't been able to, I've been distracted a few times, but it's gonna be done soon. And so you can see the outcome soon.
All right, so let's thank Kevin for the very nice talk, and let's move on to the next speaker, who is Johanna Teske from Carnegie EPL, and her title is The Role of a Sample Selection in Understanding Exoplanet Atmospheres as a Population, a Case Study. Johanna, you can turn on your video and the floor is yours.
Okay, great. Thanks for the opportunity to talk about this work in progress. This is in collaboration with Natasha Battaglia and Angie Wolfgang, and they're really the leads of this work. So I will try to answer questions, but I'll encourage you to also watch out for a paper that we're working on. So the motivation here is we're interested in understanding small planets like those detected by TESS as a population, and thus might have some biases to worry about in understanding multiple planets in this way. And so everyone's familiar with detection bias, right? Due to limitations of observational techniques and like the transit probability, we'll just miss some parts of any given population. And those are the types of biases that occurrence rate studies try to account for. There's also what I'll investigate in this study, what I'm calling target selection bias, which is you might miss parts of the underlying population depending on which targets you select to follow up for the atmospheric characterization. So in this little cartoon, I've missed the large purple planets by only focusing on this small part of the parameter space. And also robust statistical analysis, like drawing conclusions from a population, from an observed sample about a population is challenging if you don't have a quantitative selection process. And then finally, something I'm calling observation bias, which I'm representing here by increasing the sizes of these dots, suggesting an observational technique that is biased towards detecting larger signals. And this can happen in exoplanet mass measurement observations. I'm not going to talk about that so much today, but these last two biases were also motivations for a survey that we've been conducting to follow up test planets to get their masses with PFS on Magellan, called the Magellan Test Survey. But again, we're talking about atmospheres here. So we want to go beyond just masses and radii and understand the formation, evolution of these small planets based on their atmospheric compositions that can have these different origins and be influenced by all these different effects in this great paper. So motivated by kind of the RV survey approach, trying to address some biases and wanting to understand exoplanet atmospheres and their connection to the exoplanet interiors, we wanted to study how target selection could influence results or inferences that we would make based on for the population. And so the first step was to choose a population relation to inject into a mock survey. We chose something that was kind of scientifically compelling, the C to O ratio, which might be indicative of the oxidation state of the planet if you're measuring it in the atmosphere, and we think will also be feasible to constrain with observations. And here we're choosing a fairly simple logistic relation that classifies a planet as having a carbon or oxygen dominated atmosphere depending on its radius and insolation flux. And note that it's not the C to O ratio, but the probability that the C to O ratio is less than 1 versus greater than 1, the ratio of those. And so you can sort of think of this as a 3-dimensional plane where we're saying planets are going to be above or below this C to O ratio. And to define our injected relation, we choose some points to specify, such that small planets at low insolation flux, we think will have more oxygen-dominated atmospheres. And as you go to larger insolation fluxes or bigger planets, the proportion of the planets that are at higher C to O ratios grows. So this is just made up. There's not a lot of, we don't have planets between 1 and 3 Earth radii in our solar system to rely on for what we should expect. But this is just a simplistic relation that we decided to use for this paper. And we choose our different target samples to test that effect. So the first one is just something very quantitative. We start with the sample from our MTS, radial velocity survey, and that's our selection function, and then make another cut on that based on here Tx is JDUS T expected exposure time. to reach 30 ppm precision at 4 microns with near spec. And also consider other variables like the planet radius and the stellar effective temperature. So that's one sample. The other is what we're calling the low-hanging fruit sample, where we take all the confirmed small planets with measured or even upper limits on masses. We make a grid, so the lines are sort of here and here. And then in each of those 3 radius boxes, we pick 4 targets that have the lowest exposure times, again, calculated in this same way. And then we have a third sample we wanted to try, which I'm calling evenly spaced by eye, which has the same parent sample as the lowest hanging fruit sample, but we sort of just picked the targets by eye. We filtered them based on the exposure time, but then we sort of tried to span the parameter space, but not in a super quantitative way. So with the population relation and our defined planets, we then compute Natasha computes the transmission spectra using Picasso and then uses Pandexo to compute the simulated JDOST near spec observations. And then performs abundance retrievals on those. These are just kind of cartoony versions right now of these plots, just very preliminary. I just wanted to give you an idea of what it looks like. But the takeaway is sort of here, where we want to compare what population level parameters from this model we retrieve from our simulated planets versus what we injected. And this is work by Angie using hierarchical Bayesian framework. And so here I'm showing an example of a 3D contour plot instead of like the normal corner 2D plot. The color is the density of points, and the red lines show the retrieved values. And a summary of these types of plots is shown here on the right. So this top plot is for each sample and trial, the volume of the posterior that's ruled out by the 3 sigma retrieved values. So this is kind of how precisely we are constraining the parameters, and a higher value is better. So you can see each of the different samples here. And then the bottom plot is more analogous to accuracy. It's how well we're matching the injected true values across the 3D space versus, again, the normal 2D corner plots. And so here lower is actually better. And the horizontal lines are the averages for each sample, although we omitted trial 3, something weird is happening there. So right now, this is a limited set of trials. It appears that maybe the MTS, that sample selection looks slightly better, but these lines are really close together. So I think for now, we're not sure there's really a definitive winner. So next we want to run more trials and also try slightly different atmospheric assumptions, and also try reducing the errors on our atmosphere abundance ratios that have been retrieved to see where it might start to make a difference. But importantly, something I failed to mention before was that there's actually a lot of overlap between the planets in these samples. Something like 5 to 7 planets are common between the different samples. So it may just be that we need more small planets with mass measurements, need a bigger sample to choose from to really see the effect of sample selection in the population parameters. So this is the takeaway. There's lots of caveats and we still have some tests to run, but I'll end there and I'm happy to take questions.
Thank you, Johanna, for the nice talk. Any questions from the audience? I see none at the moment, so I'll pause. Okay, let me ask one that kind of puzzled me, which is that you go for certain subpopulations and then test out like a few almost, whereas I guess in an ideal situation, I guess maybe you're right, because it takes, I guess, finite and a lot of time to actually run the simulation. So you don't have the luxury of trying this for maybe 1,000 different subsamples, right? Otherwise, you could just do a simple bootstrap of jackknife.
Yeah, we also, I mean, we're interested, I guess, you're thinking like trying just a bunch of different random samples of the subpopulation. Yeah, I think we're actually interested in how you're choosing your sample. And so this one is, I guess, not completely random. There's still like, we're filtering this a little bit. So I guess we could also try to test a random sample, but we're interested in how the decisions you make about what goes into your sample affect your results.
Yeah, makes sense. Okay, any other questions? Okay, I guess not. Then let's thank Johanna for her talk. And then we will move on to the next talk of the day, which will be given by Daniel Apai from University of Arizona. And his title is TESS Observations of Atmospheric Jets and Zonal Circulation in Ultracool Atmospheres. So Daniel, you can start your slideshow. Yes. So please take it away.
Thank you. Can you hear me well? Can you see the slides?
We can see some nice picture, I guess, yeah.
Okay, thank you. So, yeah, so this talk is about jets and zonal circulation in ultracool atmospheres. And this is a project that I completed with Domenico Nardiello and Luigi Pedin. And it was published earlier this year. So I refer you to the paper for details. I will just keep this short today. So very simply put, the question that we were after in this study is, how do brown dwarfs and directly imaged planets look like? This may sound like an obvious question. You may assume that we know the answer to this, but if you look through public domains or press releases, how brown dwarfs and directly imaged are represented, you will actually find a surprising variety of images. And that is really reflecting our lack of understanding of these atmospheres in some level. So answering this question, how do brown dwarfs look like? Of course, the goal is not to inform just simply artists' impressions, but to really understand also how do directly imaged giant exoplanets look like, to understand to what extent can we use one-dimensional models for exoplanets, how heterogeneous these atmospheres are, what are the structures that exist in them, what are the roles of clouds in setting the atmospheric spectra and heterogeneity, and basically ultimately understanding how they appear observationally is the best way for us to constrain the interplay between clouds, atmospheric circulation, pressure temperature profiles, and chemistry. So fundamentally from theory, we have predictions that in cases in an atmosphere where the energy transport, vertical energy transport is the driver, the dominating process, those atmospheres will be vortex dominated, whereas atmospheres where rotation dominates will create jet dominated circulation. So do we have examples for this in the solar system? Of course, we all know that Jupiter has zones and bands, which are belts and bands, which are representation of the jets and zonal circulation. But interestingly, Jupiter itself also displays the other mode of circulation. Close to its poles, the circulation is vortex dominated. Close to its poles, the rotation is less important. So this is a nice example. Question is how good an example Jupiter is for directly imaged planets and brown dwarfs. So are brown dwarfs and directly imaged exoplanets vortex dominated or jet dominated? So our target in this study was Luhmann 16A and B. This is the closest brown dwarf to the solar system, slightly less than 2 parsecs away. It's a binary, so we collected data together of the two sources, but as you see, because of the different rotational periods, we are able to split those and study the two objects separately. The data that we used for this project was collected by TESS in sector 10, March, April 2019, full frame images with a 30-minute cadence, and they were reduced by Domenico Nardiello and his Pathos PSF-based photometry tool, which you hopefully caught Domenico's talk in the past day. So let me show you the data itself because time is short. What you will see here in the upper panel is the measured brightness of the brown dwarf over the entire observing campaign. In the panel below, we zoom in to 20 hours worth of data just to allow you to appreciate the fine structure that is important. And in the lower right corner, you will see the generalized Lobes-Carlo periodogram as it evolves with the increasingly larger signal to noise. You can see changes taking place. As an indicator, this is a single rotation of Luhmann 16b. You actually see many rotations in this light curve. There are over 100 rotations. of Luhmann 16b. It looks first as a noisy light curve, but as I will show you later, in fact, a very simple model captures almost all of its variation. It is actually not a noisy light curve. It is just undersampled because of the cadence of tests of the full frame images. Is now a gap due to data tunneling. Let me point out in the lower right that you can see the Lomskargo periodogram already indicating multiple peaks. So the brown dwarfs are now required. You can see on the Lomskargo periodogram that there's not just one peak, but in fact, we detect multiple peaks. And the important, of course, aspect of this is that we find fine structure in those peaks in the periodogram. So we identified basically, first off, right off, two large peaks. One corresponds to Luhmann 16A. We already had priors on its rotation period, and the other corresponds to Luhmann 16b. Notably, these are not single peaks, but there's a fine structure below. So we of course went through the exercise of assessing what may be artificial signals and noises, but we could exclude any of these peaks as an artificial signal of any sort. Let me show you the fine structure, which is perhaps the most exciting aspect of the study. On the upper right, you see in blue the actual data in the periodogram. And then below in green, you see different models, all very simple models. We are basically adding a single sine wave or two, 1, 3, 4, or 6 sine waves. And you see that with additional sine waves of different periods, we can match very well the periodogram structure, suggesting that there are distinct periods present around the central rotation period of Luhmann 16b. So this suggests that there are multiple jets rotating with different velocities. So can we use this? Can this explain the actual light curve shape or only the periodogram? So I showed you already the light curve itself. It has a lot of rich structure. Now I show you on the left, top left panel, the entire light curve, and lower right, I will show different segments, just scanning through the light curve. For each of these segments, we fitted them with a simple model that consists only of sine waves. And you can see that in every case, whether it's a short segment or a long segment, we get an excellent fit. We can explain all these changes in the light curve just with a very simple model that corresponds to what you would see from different jets being present in the atmosphere. So this was very exciting. These results are completely consistent with the predictions or findings of the periodogram analysis. So how do these data and these results compare to Jupiter? What would we see in Jupiter? So this is the second time we'll use Cassini in this session. After Kevin's use of the data, I used here Cassini to provide a toy model for basically a periodogram as Jupiter would appear. So this is the data periodogram from Luhmann 16b. And I took wind speed measurements, directly measured wind speeds from the Cassini data for Jupiter and created from that a toy model just predicting what would be the effective period as a function of latitude, and then folding those into basically a synthetic Jupiter model. And what you see here is that qualitatively, what we predict as a period distribution for Jupiter is very, very similar to what we actually observe for Luhmann 16b, which is really great. So there is a really good support again from these wind speed measurements for the zonal circulation and jets. So what did we learn? How can we put this together? If we were to visit Luhmann 16a or b, what we would see are jets, each of which are rotating at different velocities, differential rotation. So the light zones basically are locations where thin cloud decks allow light from the interior to escape. Darker zones correspond to thicker cloud decks. Close to the equator, wind speeds will be the highest. That's where it rotates the fastest. And at higher latitudes, wind speeds will be lower. So effective periods of those structures will be longer. We have evidence in our data, although I don't have time to go into that in the polar regions, in fact, there is a vortex-dominated, a much smaller, but the vortex-dominated region that we can probe. So in short, we have now, and there was a surprise to me, I did not expect this amazing data on brown dwarfs and such cool objects from TESS, but we have what I think is the most detailed insight and perspective on atmospheric circulation, on ultra-cool atmospheres, brown dwarfs, and by extension, directly imaged planets. And I've just recently seen the new data from sector 36 and 37, which look even more amazing. I will stop there. Thank you.
Thank you, Daniel. Great talk. And Very exciting use of visuals, so well done. All right, so we have about 3 minutes for questions, and I see one already. So, oh, Brian also says, what a great animation. And could you say more about the qualitative agreement between your rotation periodograms for Jupiter and Lumen 16? The x-axis for the two objects seemed to span different ranges.
Yes, so basically here, hopefully you can, okay. So this is the figure in question. The x-axis are indeed different, and that basically these peaks, basically groups of peaks in the periodogram are centered around the reference rotation object, reference rotation period of the object. So for Jupiter, it's close to 10 hours, slightly 9 hours, 57 minutes. For Lumen 16b, it's around 5 hours, 28 minutes. There's not a single rotation period for these objects because they are not rigid bodies. So that is really the difference between the x-axis. And the range of periods that is represented here, you can use that actually to infer relative wind speeds across these atmospheres. You can do that for Jupiter, and you can do that also for Lumen 16b. So we have actually done that in the paper.
Cool. So the latitude at which these jets dissolve, I guess, into vortices, is there a reason to believe that that latitude should be different in brown dwarfs compared to Jupiter's?
So I think here, basically, the two fundamental parameters that will determine the mode of atmospheric circulation here fundamentally is the rotational speed and correspondingly wind speeds, level of differential rotation too, all basically linked together, and the heat transport. So for Jupiter, that has much less heat transport, much less internal energy that's being released through the atmosphere. So rotation is important at lower latitudes. For brown dwarfs, we have much more energy released because their temperature, this is around 1,100 Kelvin, but at the same time, it is also rotating faster. So I think from these two, we could directly make a model prediction for this transition latitude. We don't have yet currently a good observational way to really determine or test that, but I think we could make a pretty good prediction. It's a good question, thank you.
More questions coming up. Okay, since the rotation rate of Lumen 16 is faster, should we expect a larger number of jets as compared to Jupiter?
Yes, so actually you can work out, there's a relatively simple argument for we can use the Rhines length to figure out what would be the number of jets that you expect and get a pretty good estimate for that. We actually estimate for Lumen 16 to have more jets, about a factor of 2 more than and more zones than Jupiter.
And one more question. A truly latitudinally symmetric zonal band exhibits no light curve modulation. So how do you conclude that such structures reside on the surface?
So, okay, so basically what happens in this, and you can read the paper for me more details, is that if everything would be axisymmetric perfectly, then you would not see rotational modulations. But there are structures moving in these zonal circulation created jets. In fact, we have published a paper in 2017 in Science showing that there are large-scale waves. Just like there are waves also in Earth's zonal circulation, we have large-scale waves that propagate eastward. Basically, these waves modulate cloud thickness and introduce a rotational axisymmetry that we can trace.
Okay, thank you. Yeah, the last 2 questions, not to forget, were from David Baker and Michael Gulli Santiago. I see no other questions, and we are timed. So let's thank Daniel again for this very nice talk.
Thank you very much.
And then move on to the next speaker. Our next speaker is Néstor Espinoza. Néstor is going to talk about a test view of evenings and mornings on distant exoplanets, and he's from STSCI. So please take it away, Néstor.
Yeah, can you see my screen? Can you hear me okay?
Yes,
Okay,
both.
awesome. All right, thanks for the opportunity to be here. And I'm super excited to share some of the work we've been doing on evenings and morning and distant exoplanets. As other folks have explained, and this will come as no surprise to you, when a recent news outlet that published this, exoplanets are in fact 3D objects, newsflash. So one of the most important parts of exploring exoplanets in 3D is the fact that some of our assumptions might actually change once we start looking at them the way they really are. And in particular, there's one technique, transit spectroscopy, in which this could become super important. And here's how I like to explain it with a little cartoon. So basically, during transit spectroscopy, you have the planet coming in front of the star, and then you have part of the atmosphere is transmitted, part of the starlight is transmitted to the atmosphere. But if the planet is, for example, very hot and tidally locked, like most of the hot Jupiters we've encountered in nature, then it could happen that instead of having like a common average transit spectrum, through this transmission through the atmosphere, you might actually have one spectrum from the different sides of the planet. So the morning terminator and the evening terminator, here depicted at these semicircles, they might have different material coming into them. They might have different temperatures. The evening, for example, might be hotter because there's more some material and energy coming from the day to the night. But the morning terminator, it's material and energy coming from night to the day. There might be, we've observed these kind of jets going from one side to the other. So they might have actually different spectra. Of course, this idea is not new. There's been tons of folks actually picturing this idea in 3D. This is one case, this fabulous paper by Christian Heng on HAT-P7b, in which you can see that, the gas temperature, for instance, it's different in the evening and the morning terminator. The nucleation rate, how fast you can form these clouds. And even the water abundance might change depending on which side you look at. And this has impacts on the transit spectrum like that you might be able to detect. And it depends a ton on cloud properties. So here's limb spectra from the morning and evenings computed by Paul Molière here. And if you focus, most of the bigger signatures of this come from the optical actually. So in all these models, it's always in the optical because of the cloud properties. So this Rayleigh slope goes up, creates a ton of difference in here. And this falls just in the TESS bandpass. So one of the questions that we formed was, could we detect this from TESS? It is expected, that these signatures to be all the way up to 2000 ppm differences between the depths on each side. So maybe this could be detectable. So the question is, how do you detect them? And we went, kind of the brute force thing. Next, thanks to some work that we did together with Catherine Jones, a PhD student from the University of Bern, on a recently published paper in which we explored fitting, directly light curves and tried to extract this information either from TESS or GLUST. So the idea is basically that you have a light curve model, which is two semicircles instead of this classic round circle in it. So you can form these asymmetric light curves and you can fit them directly to data. All this is in a library called Catwoman that you can go and use. It's has nicely documented. And the main idea then is that you have a transit light curve, you go and fit it with both asymmetric, like the classical Batman model, and an asymmetric, these two semicircle models, and you try to detect these limb asymmetries in order to constrain the morning and evenings on these worlds. So the big question, of course, is can TESS do this? And we explored this with some injection and recovery tests. So we injected these asymmetries with different morning to evening depth differences. That's the x-axis here, and different light curve precisions for TESS-like light curves in the y-axis. So in the parentheses is the precision you need if your target is in 13 sectors, like a continuous viewing sum target. And the non-parenthesis light curve precisions is like a 1 sector 2-minute cadence target. So it seems there's some targets out there for which this is detectable, which is the dark region. Of course, the larger the morning to evening depth difference, the easier it is to detect. So the worse precision, with worse precision, you would be able to detect it anyways. So what we just went and tried to fit TESS light curves with this model and see what comes out of it. So what I wanted to show here as a showcase of what the kind of precision that TESS is getting. So one of the beautiful cases is WAF62b. This is a light curve that Jaishil Patel prepared in one of the papers that we're about to publish, not related to the limbs asymmetries problem. It's just a general study of all the known transiting exoplanets. But for WASP-62, you can see, how beautiful the light curve is. And if you cannot see the combined precision in the middle down, I'm going to enlarge that, which because it's ridiculous, is a precision of 32 parts per million on the transit depth, which is, extremely precise. And there's a handful of targets for which TESS is actually improving the precision that you can get from these transit light curves. So here's what these 20 sectors worth of data for WASP-62P look like. So the precision that you can get once you face all the light curves is in the order of 70 parts per million per 2-minute bins. That's beautiful. That's like GLUST-like precision. It's incredible. And actually, you can kind of constrain the morning to the evening minus morning depths to be about 600 parts per million with an error of around 1,000 parts per million. So we're not quite there yet to say that this is happening or not, but we are getting to constraints on this. And this precision can actually be better. Right now, we're using the PDC SAP light curves, but we've been exploring with pixel level decorrelation. It turns out that gives you even better precision. Once you start exploring other light curves, like for example, here's WASP-121 from just 3 sectors. You have here WASP-126b, 13 sectors. One of the things that we've started to see in all these light curves, whenever we try this, is that the data always comes with the following fact, that it seems that the evening limbs are always larger than the morning limbs. That would make sense if they're hotter, for instance. So that's something that we want to explore now that we're fitting all these set of light curves and ask the question that on average, can we do a population study similar to what Sheets and Deming did in 2017 in order to explore the evenings and limbs as a population of all the hot Jupiters in TESS. So finally, I just want to leave you with the summary. So basically, we're just exploring the TESS evening and morning limbs of exoplanets as seen from TESS, sorry. If you have any questions, I'll be welcome to answer them. Thank you.
Thanks, Néstor. Great talk. All right, so any questions from the audience? I see someone is typing, so we'll, I think, have soon a question. Maybe until then, let me squeeze in one. So is this type of search degenerate to some extent with searches that look for perturbations from sphericity or circularity of the transitor, especially in the context of SETI?
Right. So you're asking if if the planet has a weird shape, would that be degenerate with what we're trying to find? Is that the question?
Yes, exactly.
Yeah. So at least from rings and like oval-like shapes of planets, that leaves like an entire slope in the entire light curve. If you like fit a normal symmetric model and then you subtract it to the data, that leaves like a slope in the data. But the limb asymmetries, as you can see them here in the residuals, like the red curve in the bottom, it's always in ingress and egress. So that's the beauty of this. That it's most of the signal just happens there. I wonder if as we get to better precisions, they will start to be differentiated. But as a population, I would see how that could be one issue. Yeah.
Sounds good. Okay, so we have one question from Brian Jackson. How sensitive are your results to the limb darkening parameters?
Oh, they're not sensitive at all. So we're leaving the limb darkening coefficients free. And actually in the simulations that I showed you, that these detectability maps that I showed you before, this one, sorry, just passed it through with full speed. But in the detectability maps that we made, the limb darkenings were free parameters. So it's not an issue.
Okay, one more question before we close. Also, could you say something about your remark that PLD might give better precision than PDC SAP? Are you using the light curve PLDs?
No, we're computing the entire thing simultaneously. So we simultaneously fit for the PLD coefficients, a Gaussian process on top to get rid of any stellar activity, and the transit model. So it's a huge fit. Like for WASP-62b, for example, it's like 200 free parameters. But it's doable if you have the right tools. Yeah.
Okay, that's great. So So let's thank Néstor for the very nice talk, and then move over. So the next talk will be given by Dimitra Atri from NYU Abu Dhabi. And then let me just make a reminder that we need to pause recording at this point. So last talk of the day by Alex Hindle, and I think it's also late for him. So thanks for the availability. And his title, well, he's from Newcastle University, and his title is Magnetically-driven hotspot reversals in ultra-hot Jupiter atmospheres. The floor is yours.
Great, thanks, Tansi. Sorry, let me just get it all on full screen. Here we go. Yeah, late, not quite 1 a.m. though, so I feel lucky there. Thanks very much, Tansi, and thanks for all the organisers. It's great to follow such interesting talks. Apologies first, I feel like I should apologise for anyone that came to my talk in a previous session, the ultra short period planet session, because this talk will be fairly similar, but hopefully you'll find it just as interesting the second time around. For those that don't know me, I'm Alex Hindle. I'm a postdoc at Newcastle University, and I've been working with Tammy Rogers and Paul Bushby, and I'll be working with them until 2023. Today I'm going to talk about some work that I carried out during my PhD with them, and it's resulted in 2 recently accepted publications down here. Okay, so let's go over the problem. So until recently, phase curve measurements of hot Jupiters have universally found eastward hotspot offsets. Such observations agree with hydrodynamic theory, which always predicts eastward hotspots, as illustrated in this solution from Sherman and Pavani. However, recent studies have identified 5 hot Jupiters with either westward hotspots or oscillatory east-west hotspots. 4 of these are ultra-hot Jupiters, whereas CoRo 2b is cooler and is kind of the exception here. There are 3 explanations that have generally been proposed. One is cloud asymmetries confounding observations. However, some recent work from Heng et al. Has suggested that the day side of ultra-hot Jupiters might be so hot that they could vaporize as clouds, making this not so much of a problem. Second, non-synchronous rotation offers an explanation. However, this doesn't really agree with tidal theory of ultra-hot Jupiters, which, because of their near-zero eccentricities, are expected to have one-to-one tidal lock-in. Finally, hotspot oscillations have been predicted in 3D MHD simulations, but the mechanisms driving them until now is not well understood. So our goal was to develop an understanding of the magnetic mechanism that can trigger the reversals using a reduced physics shallow water model, or shallow water MHD model. In the bottom panel, I provided schematic example solutions displaying hotspot reversals. Okay, but I appreciate not everyone's a magnetic expert. So before explaining the mechanism, let's go over some magnetic field geometry in hot Jupiter atmospheres and what they look like. So in 3D simulations, they've shown equatorially antisymmetric toroidal fields dominate the hottest hot Jupiter atmospheres. And as we can see in these bottom 2 panels from Rogers and Komacek. Why does this happen? Well, hydrodynamic theory predicts strong zonal flows in hot Jupiters, but these hot Jupiters have partially ionized atmospheres. So as these flows pass through a deep-seated magnetic field, an atmospheric toroidal field gets wound up. So the magnitude of this toroidal field scales proportionally to the planet's deep-seated magnetic field. So down here, we've got the scaling law, and this thing RM, which is directly proportional to the conductivity, which is highly temperature dependent. So in cooler planets, toroidal field is weak, so magnetic solutions behave similar to their hydrodynamic counterparts, whereas in hotter planets, toroidal field is strong and complex magnetic behaviors, including hotspot oscillations, can emerge. Okay, so what do we find? What triggers these hotspot reversals? So let's go back to hydrodynamics, as we always do in MHD. So Shomafani showed that drag-adjusted geostrophic circulations cause eastward hotspots by transporting thermal energy from the western equator up to mid to high latitudes and back down to the eastern equator. This transport causes an eastward hotspot shift, and the same circulations also drive equatorial superrotation by a similar momentum transporting process that follows the same structures. What a strong toroidal field does is it obstructs these circulations. The obstructions of these circulations will cause a kink in the magnetic field and in these toroidal magnetic field lines, and if we have equatorward bending and an antisymmetric field, we always get a westward Lorentz force acceleration. due to the way that magnetic tension works. This eventually drives hotspots westwards, sorry. And so the combination of blocking in the meridional direction of these flows and a westward shift creates these structures where we have zonally aligned westward hotspots. Okay, in the same work, we use our understanding of the mechanism to pull out a physically motivated reversal criteria, and we compare this to simulations and find that the scaling law compares reasonably well, so that's good news. This predicts the threshold in terms of toroidal field. However, most astrophysicists are interested in the dipole field strength. So we kind of back put in this scaling law that I've already mentioned into some real data and find a dipole, critical dipole threshold. Okay, so here we plot the critical dipole field strength speed dip crit again on a log scale against some equilibrium temperatures for hot Jupiters in the exoplanet.eu dataset. The two lines here, we have one at 14 Gauss, which is for Jupiter's dipole field strength, and one at 28 Gauss, which is just double that. So these are reference lines that we can kind of compare to something that's observationally motivated in our solar system. As expected, we find a general trend of B-dip crit decreasing rapidly against temperature as ionization increases, meaning that cooler hot Jupiters need a stronger deep-seated planetary field for magnetic reversals to occur. This trend is caused by conductivity increasing with temperature. So the plot splits into three clear regions. We have cool hot Jupiters, which are weakly ionized and require unfeasibly large dipole field strengths for reversals. An example of this is CoRo 2b, which requires approximately 3 kilogauss dipole magnetic field strength, which is huge. So we conclude that it's most plausible that the observations of CoRo 2b are linked to a non-magnetic origin. On the right, we've got the ultra hot Jupiters. Of these, we've got the remaining 4 westward hotspot / bright spot observations. That they can all be explained by weak to moderate planetary magnetic field strengths. So if we can rule out the non-magnetic explanations on these planets, we can directly place constraints on the lower bounds of planetary magnetic fields. So that's really interesting. Also, should highlight, if you're a modeler, this suggests that on these ultra hot Jupiters, linear drags aren't sufficient to treat the MHD, because they suggest that we've just got a drag, we've not got something that can fully reverse a flow. So they don't include complex MHD. So you need to start putting in the self-consistent MHD treatment here, unfortunately. So in the intermediate range, that's probably the most interesting, because it can indicate a typical magnetic field strength of hot Jupiter atmospheres by providing where kind of a cutoff and where we stop getting observations into the far future once we've populated this plot. Excitingly for TESS astronomers, we can use these results to guide future work. So once we have foreknowledge of the hot Jupiters that are likely to exhibit hotspot oscillations, we can start to plan our studies around our a priori knowledge. So this is some work that we're planning on doing with Brian Jackson, or we've already started, Brian Jackson, Elizabeth Adams. And here are some hot Jupiters of interest that we're particularly interested in based on what you've previously seen and our constraints. So I've put in some B-dip crits for these planets. So you see they go through a range of dipole field strengths. So one thing to note if you're using TESS is that HAP-P7b and Kepler-76b have observed bright spot oscillations on 10 to 100 days. So you've got to use, if you want to observe the full oscillations, you want to be using long time studies. So you could just miss this if you're looking at a short time study. So that could potentially be a problem with TESS if you're on the 100-day side of the spectrum. So here's a plug for our paper. In here, I've highlighted 65, sorry, I can't read, hot Jupiters of interest in the paper and tabulated below. And I'm planning on putting a full list up on a website or something. If you're interested in doing something like this, just email me and I can give you some planets that you're interested in. Cool. And just if there are any questions, that's all I have.
Thank you, Alex. Nice talk. So let's see. Yes, Brian Jackson has a question. Can you say something about how only using linear magnetic drag in a GCM will incorrectly predict phase curves?
Yeah, so so the problem with these treatments is that it treats the Lorentz force as a drag, and it's not a drag. It's a complex acceleration that is caused by the magnetic field geometry of, yeah, it's caused by magnetic field geometry, and it's highly nonlinear. So for instance, a linear drag treatment, you can only ever get hotspots going to an offset of 0, so at the substellar point, whereas this theory actually predicts that you do get westward hotspots. And in fact, they oscillate. So yeah, so if you just use a linear drag, you wouldn't get oscillations and you wouldn't get westward hotspots. As we are moving towards the point of criticality, you do get a shift in a similar way to a linear drag, but once you overcome that threshold, you start getting more complex time-dependent MHD behavior, so which looks quite different from the hydrodynamics.
That's great. So quick question from my side, because something that I worked on kind of relates to this. So what's your take on underlying dynamics unrelated to magnetism that can cause westward phase shifts, like clouds, nocturnal clouds on the Western hemisphere, for example?
So I don't know tons about clouds. The idea of clouds, right, is more to do with the fact that they cause reflections in your light curves, right? It's not that they actually are hotter regions. So I think that's, I mean, it's still very much like an active field, right? Working out whether these can explain such oscillations in your phase curves. But I mean, the shorter period planets, the hotter they get, the more the clouds are getting vaporized on the day side. So so I'm not entirely sure. I mean, in the paper Helling et al. 2020, they did rule that out for HAT P7b as an explanation. But there's, yeah, I wouldn't like to comment more generally. But I think they did a similar thing for, I think it was at WASP 18b, I think, in a different paper the year before. So there are some suggestions that it might be the case for other ultra-hot Jupiters.
Yeah, yeah, I think there's no consensus, so I think it's all open to interpretation. There are multiple targets that do that. Anyway, so great talk. Thank you so much. And I'd like to take this opportunity to thank all the speakers in the session. I think this was very useful and exciting to hear the progress in the field that TESS is contributing to. So before we close, I'll just make a quick reminder that—
Sorry, can I just say one thing?
Oh, yes, please.
So one thing about MHD that is potentially indifferent to cloud observations that Brian found in his measurements of Kepler 76b is that there's a correlation between when the hotspot time correlation, when the hotspots go westward, the observed brightness goes up, which is what you would expect with this mechanism, because that's at the point where you've got your zonal flows being completely confined by the magnetic field. So we're not allowing sort of meridional transport. So that's confining it's confining your temperature transporting flows. So you expect, and you find this in simulations, a brightness increase at the time where they reverse. So that's potentially one way that we could spot the difference, but it's very tricky, right?
Yeah.
Yeah. Sorry.
Yeah, I think it's a very interesting degeneracy, though. Yeah. Yeah. Thanks for that clarification. All right. So yes, let's thank all the speakers. I'm just going to end with a quick reminder that tomorrow we're restarting at 9 a.m. East Coast time. And the session will be on solar system and new missions. And So with that, let's thanks the speakers again, and I hope to see you tomorrow. Bye, everyone.